Topology is the mathematical study of shapes and topological spaces. It is an area of mathematics concerned with the properties of space that are preserved under continuous deformations including stretching and bending, but not tearing or gluing. This includes such properties as connectedness, continuity and boundary. Topology developed as a field of study out of geometry and set theory, through analysis of such concepts as space, dimension, and transformation. Such ideas go back to Leibniz, who in the 17th century envisioned the geometria situs and analysis situs. The term topology was introduced by Johann Benedict Listing in the 19th century, although it was not until the first decades of the 20th century that the idea of a topological space was developed. By the middle of the 20th century, topology had become a major branch of mathematics. Topology has many subfields. General topology establishes the foundational aspects of topology and investigates properties of topological spaces and investigates concepts inherent to topological spaces. It includes point set topology, which is the foundational topology used in all other branches. Algebraic topology tries to measure degrees of connectivity using algebraic constructs such as homology and homotopy groups. Differential topology is the field dealing with differentiable functions on differentiable manifolds. It is closely related to differential geometry and together they make up the geometric theory of differentiable manifolds. Geometric topology primarily studies manifolds and their embeddings in other manifolds. A particularly active area is low-dimensional topology, which studies manifolds of 4 or fewer dimensions. This includes knot theory, the study of mathematical knots. See also, topology glossary for definitions of some of the terms used in topology, and topological space for a more technical treatment of the subject. History. Topology began with the investigation of certain questions in geometry. Leonhard Euler's 1736 paper on the 7 bridges of Karl Paragraph Nyxberg is regarded as one of the first academic treatises in modern topology. The term topology was introduced in German in 1847 by Johann Benedict Listing in Verstudien zur Topologie, who had used the word for 10 years in correspondence before its first appearance in print. The English form topology was first used in 1883 in Listing's obituary in the journal Nature to distinguish qualitative geometry from the ordinary geometry in which quantitative relations chiefly are treated. The term topologist in the sense of a specialist in topology was used in 1905 in the magazine Spectator. However, none of these uses corresponds exactly to the modern definition of topology. Modern topology depends strongly on the ideas of set theory, developed by Georg Cantor in the later part of the 19th century. In addition to establishing the basic ideas of set theory, Cantor considered point sets in Euclidean space as part of his study of Fourier series. Henri Poincaré copyright published Analysis Situs in 1895, introducing the concepts of homotopy and homology, which are now considered part of algebraic topology. Unifying the work on function spaces of Georg Cantor, Vito Volterra, Serre Arslan, Jacques Audemard, Giulio Ascoli and others, Maurice Farr copyright Chet introduced the metric space in 1906. A metric space is now considered a special case of a general topological space. In 1914, Felix Hausdorff coined the term topological space, and gave the definition for what is now called a Hausdorff space. Currently, a topological space is a slight generalization of Hausdorff spaces, given in 1922 by Kazimierz Kuratowski. For further developments, see point set topology and algebraic topology. Elementary introduction. Topology as a branch of mathematics can be formally defined as the study of qualitative properties of certain objects that are invariant under a certain kind of transformation, especially those properties that are invariant under a certain kind of equivalence. To put it more simply, topology is the study of continuity and connectivity. Topology is also used to refer to a structure imposed upon a set X, a structure that essentially characterizes the set X as a topological space by taking proper care of properties such as convergence, connectedness and continuity, upon transformation. Topological spaces show up naturally in almost every branch of mathematics. This has made topology one of the great unifying ideas of mathematics. The motivating insight behind topology is that some geometric problems depend not on the exact shape of the objects involved, but rather on the way they are put together. For example, the square and the circle have many properties in common. They are both one-dimensional objects and both separate the plane into two parts, the part inside and the part outside. One of the first papers in topology was the demonstration, by Leonhard Euler, that it was impossible to find a route through the town of Karl-Paragraph-Nixburg that would cross each of its 7 bridges exactly once. This result did not depend on the lengths of the bridges, nor on their distance from one another, but only on connectivity properties, which bridges are connected to which islands or river banks. The 7 bridges of Karl-Paragraph-Nixburg is a famous problem in introductory mathematics, and led to the branch of mathematics known as graph theory. Similarly, the hairy ball theorem of algebraic topology says that one cannot comb the hair flat on a hairy ball without creating a cowlick. This fact is immediately convincing to most people, even though they might not recognize the more formal statement of the theorem, that there is no non-vanishing continuous tangent vector field on the sphere. As with the bridges of Karl-Paragraph-Nixburg, the result does not depend on the shape of the sphere. It applies to any kind of smooth blob, as long as it has no holes. To deal with these problems that do not rely on the exact shape of the objects, one must be clear about just what properties these problems do rely on. From this need arises the notion of homeomorphism. The impossibility of crossing each bridge just once applies to any arrangement of bridges homeomorphic to those in Karl-Paragraph-Nixburg, and the hairy ball theorem applies to any space homeomorphic to a sphere. Intuitively, two spaces are homeomorphic if one can be deformed into the other without cutting or gluing. A traditional joke is that a topologist cannot distinguish a coffee mug from a donut, since a sufficiently pliable donut could be reshaped to a coffee cup by creating a dimple and progressively enlarging it, while shrinking the hole into a handle. A precise definition of homeomorphic, involving a continuous function with a continuous inverse, is necessarily more technical. Homeomorphism can be considered the most basic topological equivalence. Another is homotopy equivalence. This is harder to describe without getting technical, but the essential notion is that two objects are homotopy equivalent if they both result from squishing some larger object. An introductory exercise is to classify the uppercase letters of the English alphabet according to homeomorphism and homotopy equivalence. The result depends partially on the font used. The figures use the sans serif myriad font. Homotopy equivalence is a rougher relationship than homeomorphism. A homotopy equivalence class can contain several homeomorphism classes. The simple case of homotopy equivalence described above can be used here to show two letters are homotopy equivalent. For example, O fits inside P and the tail of the P can be squished to the whole part. Homeomorphism classes are no holes 3 tails, no holes 4 tails, 1 hole no tail, 1 hole 1 tail, 1 hole 2 tails, 2 holes no tail, and a bar with 4 tails. Homotopy classes are larger, because the tails can be squished down to a point. They are 1 hole, 2 holes, and no holes. To be sure that the letters are classified correctly, we need to show that two letters in the same class are equivalent and two letters in different classes are not equivalent. In the case of homeomorphism, this can be done by selecting points and showing their removal disconnects the letters differently. For example, X and Y are not homeomorphic because removing the center point of the X leaves 4 pieces. Whatever point in Y corresponds to this point, its removal can leave at most 3 pieces. The case of homotopy equivalence is harder and requires a more elaborate argument showing an algebraic invariant, such as the fundamental group, is different on the supposedly differing classes. Letter topology has practical relevance in stencil typography. For instance, braggadocio font stencils are made of one connected piece of material. Important concepts in topology, topologies on sets. The term topology also refers to a specific mathematical idea which is central to the area of mathematics called topology. Informally, A topology is used to tell how elements of a set are related spatially to each other. The same set can have different topologies. For instance, the real line, the complex plane, and the Cantor set can be thought of as the same set with different topologies. Formally, let X be a set and let I be a family of subsets of X. Then I is called a topology on X if both the empty set and X are elements of I, any union of elements of I is an element of I, any intersection of finitely many elements of I is an element of I. If I is a topology on X, then the pair is called a topological space. The notations I may be used to denote a set X endowed with a particular topology I. The members of I are called open sets in X. A subset of X is said to be closed if its complement is an I. A subset of X may be open, closed, both, or neither. The empty set and X itself are always both closed and open. An open set containing a point X is called a neighborhood of X. A set with a topology is called a topological space. Continuous functions and homeomorphisms. A functional map from one topological space to another is called continuous if the inverse image of any open set is open. If the function maps the real numbers to the real numbers, then this definition of continuous is equivalent to the definition of continuous in calculus. If a continuous function is one-to-one and onto, and if the inverse of the function is also continuous, then the function is called a homeomorphism and the domain of the function is said to be homeomorphic to the range. Another way of saying this is that the function has a natural extension to the topology. If two spaces are homeomorphic, they have identical topological properties, and are considered topologically the same. The cube and the sphere are homeomorphic, as are the coffee cup and the donut. But the circle is not homeomorphic to the donut. Manifolds. While topological spaces can be extremely varied and exotic, many areas of topology focus on the more familiar class of spaces known as manifolds. A manifold is a topological space that resembles Euclidean space near each point. More precisely, each point of an n-dimensional manifold has a neighborhood that is homeomorphic to the Euclidean space of dimension n. Lines and circles, but not figure eights, are one-dimensional manifolds. Two-dimensional manifolds are also called surfaces. Examples include the plane, the sphere, and the torus, which can all be realized in 3 dimensions, but also the Klein bottle and real projective plane which cannot. Topology topics. General topology. General topology is the branch of topology dealing with the basic set theoretic definitions and constructions used in topology. It is the foundation of most other branches of topology, including differential topology, geometric topology, and algebraic topology. Another name for general topology is point set topology. The fundamental concepts in point set topology are continuity, compactness, and connectedness. Intuitively, continuous functions take nearby points to nearby points. Compact sets are those which can be covered by finitely many sets of arbitrarily small size. And connected sets are sets which cannot be divided into two pieces which are far apart. The words nearby, arbitrarily small, and far apart can all be made precise by using open sets, as described below. If we change the definition of open set, we change what continuous functions, compact sets, and connected sets are. Each choice of definition for open set is called a topology. A set with a topology is called a topological space. Metric spaces are an important class of topological spaces where distances can be assigned a number called a metric. Having a metric simplifies many proofs, and many of the most common topological spaces are metric spaces. Algebraic topology. Algebraic topology is a branch of mathematics that uses tools from abstract algebra to study topological spaces. The basic goal is to find algebraic invariants that classify topological spaces up to homeomorphism, though usually most classify up to homotopy equivalence. The most important of these invariants are homotopy groups, homology, and cohomology. Although algebraic topology primarily uses algebra to study topological problems, using topology to solve algebraic problems is sometimes also possible. Algebraic topology, for example, allows for a convenient proof that any subgroup of a free group is again a free group. Differential topology. Differential topology is the field dealing with differentiable functions on differentiable manifolds. It is closely related to differential geometry, and together they make up the geometric theory of differentiable manifolds. More specifically, differential topology considers the properties in structures that require only a smooth structure on a manifold to be defined. Smooth manifolds are softer than manifolds with extra geometric structures, which can act as obstructions to certain types of equivalences and deformations that exist in differential topology. For instance, volume and Riemannian curvature are invariants that can distinguish different geometric structures on the same smooth manifold. That is, one can smoothly flatten out certain manifolds, but it might require distorting the space and affecting the curvature volume. Geometric topology. Geometric topology is a branch of topology that primarily focuses on low-dimensional manifolds and their interaction with geometry, but it also includes some higher-dimensional topology. Some examples of topics in geometric topology are orientability, handle decompositions, local flatness, and the planar and higher dimensional paragraph NFLIES theorem. In high-dimensional topology, characteristic classes are a basic invariant, and surgery theory is a key theory. Low-dimensional topology is strongly geometric, as reflected in the uniformization theorem in 2 dimensions. Every surface admits a constant curvature metric. Geometrically, it has one of 3 possible geometries: positive curvature spherical, zero curvature flat, negative curvature hyperbolic. And the geometrization conjecture in 3 dimensions. Every 3 manifold can be cut into pieces, each of which has one of 8 possible geometries. 2-dimensional topology can be studied as complex geometry in one variable. By the uniformization theorem, every conformal class of metrics is equivalent to a unique complex one, and 4-dimensional topology can be studied from the point of view of complex geometry in 2 variables, though not every 4 manifold admits a complex structure. Generalizations. Occasionally, one needs to use the tools of topology, but a set of points is not available. In pointless topology, one considers instead the lattice of open sets as the basic notion of the theory, while Grothendieck topologies are structures defined on arbitrary categories that allow the definition of sheaves on those categories, and with that the definition of general cohomology theories. Applications of topology. Biology, not theory, a branch of topology, is used in biology to study the effects of certain enzymes on DNA. These enzymes cut, twist, and reconnect the DNA, causing knotting with observable effects such as slower electrophoresis. Topology is also used in evolutionary biology to represent the relationship between phenotype and genotype. Phenotypic forms which appear quite different can be separated by only a few mutations depending on how genetic changes map to phenotypic changes during development. Computer science. Topological data analysis uses techniques from algebraic topology to determine the large-scale structure of a set. The main method used by topological data analysis is, replace a set of data points with a family of simplicial complexes, indexed by a proximity parameter. Analyze these topological complexes via algebraic topology, specifically, via the theory of persistent homology. Encode the persistent homology of a dataset in the form of a parameterized version of a Betti number, which is called a barcode. Physics. In physics, topology is used in several areas such as quantum field theory and cosmology. A topological quantum field theory is a quantum field theory which computes topological invariants. Although TQFTs were invented by physicists, they are also of mathematical interest, being related to, among other things, knot theory and the theory of 4 manifolds in algebraic topology, and to the theory of the moduli spaces in algebraic geometry. Donaldson, Jones, Witten, and Kontsevich have all won Fields medals for work related to topological field theory. In cosmology, topology can be used to describe the overall shape of the universe. This area is known as space-time topology. Robotics. The various possible positions of a robot can be described by a manifold called configuration space. In the area of motion planning, one finds paths between 2 points in configuration space. These paths represent a motion of the robot's joints and other parts into the desired location and pose. See also equivariant topology, general topology, list of algebraic topology topics, list of examples in general topology, list of general topology topics, list of geometric topology topics, list of topology topics, publications in topology, topology glossary, references. Further reading, Rissard and Jelking, General Topology, Helderman Verlag, Sigma Series in Pure Mathematics, December 1989, ISBN 3-88538-006-4. Bourbaki. Elements of Mathematics, General Topology, Edison Euro Wesley. Breitenberger, E. Johann Benedict Listing. In James, I.M. History of Topology. North Holland. ISBN A978-0-444-82375-5. Kelly, John L. General Topology. Springer Verlag. ISBN A0-387-90125-6. Brown, Ronald. Topology and Groupoids. Booksurge. ISBN A1-4196-2722-8. Wikierskiewski, General Topology, Dover Publications, 2000, ISBN 0-486-41148-6. Pickova, Clifford of the Marr Paragraph Bias Strip, Dr. August Marr Paragraph Bias's Marvelous Band in Mathematics, Games, Literature, Art, Technology, and Cosmology. Thunder's Mouth Press. ISBN A1-56025-826-8. External links, Haswinkel, Michiel, ed., Topology, General, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4. Elementary Topology, A First Course Vero, Ivanov, Netsvetov, Kharlamov. Topology at DMOZ, the Topological Zoo at the Geometry Center. Topology Atlas, Topology Course Lecture Notes Aisling McCluskey and Brian McMaster, Topology Atlas. Topology Glossary, Moscow 1935, Topology Moving Towards America, a historical essay by Hassler Whitney.